Alrighty, the last video of this little series puts a twist on the last problem. I'm going to have the same box. He's going to have the same mass, and he's going to be on the same type of surface, so the coefficient of friction is also going to be the same. However, in this case, I am adding a pull to him. So in the last problem, my box was on the incline, and he was simply allowed to slide down. Now, I'm going to pull him up with 250 newtons of force at an angle of 30 degrees to the incline. And I'm going to make this one especially fun. Let's say that my incline actually has a length of 2.5 meters. He starts at the bottom at rest. And my question is, how long does it take to get to the top of the incline? Oh dear. Oftentimes, when you're working problems with forces, the acceleration you solved for is then taken to a kinematics equation to find out something else: final velocity, displacement, or time. And that's what we're going to do in this particular problem. We're going to solve for acceleration first by getting the net force acting on the box and Newton's second law of motion, using then that acceleration in kinematics formulas. Now, in this particular scenario, we would want to jump to net force. And again, I have to ask myself which forces are acting in the direction of the incline. This time there's not two. This time there's three. One, I have a force applied, but this is not the weight of the box pulling him down the incline. This is the size of my pull of that 250 newtons up the incline. I also, yes, will have the force of kinetic friction. But just because he's not the star of the show anymore doesn't mean that X component of the force of gravity isn't still in play. I have actually two forces down the incline. One, the force of friction, and a second, the part of gravity, of the weight of the object that acts in the X direction. So three forces for the net force. How do we go about grabbing those and pulling them apart? Well, getting the force applied in the X direction is not too bad. If we remember my scenario, I have a box. He's being pulled with 250 newtons at an angle of 30 degrees. Well, that part of that force that acts up the incline is the X component of the force. So 250 newtons cosine of 30. And since I haven't changed this incline, he's still 20, and I did not change the mass of the box, so the weight is the same. The component of the weight that acts in the X direction also hasn't changed. In other words, the size of this side of my triangle hasn't altered. It's still going to wind up being 134 newtons. And remember, we got that by the weight of the object, mg, sine of my angle, which was in this case 20 degrees. So the one, again, that's causing me the issue is my force of friction. But it's not really an issue if I simply take it slowly and think about what we did last time. Actually, in the last two videos. To get to friction, I'd have to go through the coefficient of friction. So we'll start there. Coefficient of friction is force of friction divided by normal force. And again, we have to work to get that normal force. Now in this case, the problem becomes a little bit more like the first one of this series, where I had an object on a horizontal surface, but he was being pulled upwards with a force. If I have an object on a horizontal surface and he's not being pushed down or pulled up, his weight is the sole player in the game in terms of producing the response force by the floor. So in other words, action force, box pushes on floor. With how much force? Its weight. Reaction force, floor pushes up on box. With how much force? Object's weight. But when I added that little twist of applying a force like this upward piece of the force had to be subtracted from the object's weight. And we have to do the same thing in this problem. My normal force would be the component of the object's weight that was directed perpendicular to the incline, or my mg cosine theta. And I would have to subtract the upward piece, or the vertical piece, of my 250 newtons. So 250 sine of 30. My normal force winds up being 244 newtons. Now, coefficient of friction, 0.15. Force of friction divided by my 244. And I wind up getting, 36.6 newtons as my oppositional force to the motion of the object. Took a little step or two, but we got there. So, going back to my idea of net force equals force applied in the x direction, 250 cosine 30, that happens to be 217 newtons. Oops, well, I'll leave the newtons off for right now. Plus the force of gravity acting in the x direction, or the component of the weight pulling the box, or trying to pull the box down the incline, mg sine theta, 134 newtons, but I cannot forget it's opposite the direction of the motion. It's down the incline as opposed to up. Either way, we're going to give him a negative. And my force of friction, which we said was 36.6 newtons. But again, that's down the incline. That opposes the motion, so we give him a negative. My net force for this particular problem winds up being 46.4 newtons. Now, Newton's second law of motion says that 46.4 newtons is equal to the mass of the object, 40 kilograms, times acceleration. So now when I solve for my acceleration, I wind up getting, well, where am I going to write them? I don't know. So I'll put them in a very obnoxious color. I'll make him orange. My acceleration, 1.16 meter per second squared. So I've really done the same sort of things. I have first set up what I needed to do to calculate net force. In other words, which forces acted in the plane of the motion of the object. And then I had to work to calculate each force. And sometimes it was pretty easy, sometimes it took a little bit more work. With net force, Newton's second law of motion takes me into acceleration. Now for the last two problems, that's been where we stopped. Here, we're not there yet. Because I wanted to go a little bit farther. I'm saying that my box is actually starting right here. And that the distance he's going to cover, delta x, is 2.5 meters. I'm saying he's starting with a velocity of 0, so he starts at rest. And I want to know how long is it going to take him to get to the top of the incline. So I have my information, delta x, 2.5 meters, v0, 0 meter per second. And I know acceleration, 1.16 meter per second squared. I want time. I asked myself, is there one formula that takes all of these three bits of information and lets me solve for that guy? And there is. Delta x is v0t plus 1/2 AT squared. Delta x, 2.5 meters. My initial velocity is 0, so that whole piece is 0. We'll just leave him out. 1/2 my 1.16 meter per second squared times time squared. Time winds up being 2.07 seconds. Wow. Seems like a lot of work, doesn't it? To ultimately just get to time. Well, if I was something like working in a factory and I had a machine that was having to lift something or drag some boxes or crates or who knows up to a loading dock, and I needed to know how long that was going to take so I could time the assembly line process, and nothing wound up getting screwed up or messed up or, you know, just sort of, I don't know, backed up along the way. Well, yeah, I need to know the net force acting on the boxes, what is the mass of the boxes, what would be the acceleration of the boxes, and therefore how long would it take to make it up from one part of the factory floor to another. I'd have to go through a very similar set of steps. So, working on these, again, be methodical, label all your information, try not to forget any forces. That's usually the problem. And watch out for any pitfalls in terms of positives or negatives as you go through.